Hello everybody, my name is Artun Sevgili and we're going to be presenting our medical imaging final project, the simulation analysis of flow-induced non-idealities in MRI using synthetic phantom data. Our group members are me, Artun Sevgili, Defne Yaskılıç, and Doğa Demirbağ. So the flow effect can be analyzed under two umbrellas. The one is the phase effects and the second is the time of flight effects. The time of flight effects can be subdivided into signal washout and inflow enhancement as well. So we here have a standard spin echo sequence. That's what we assume in our simulations. uh, in normal echoplanar imaging with spin echo, we assume uh, stationary spins. This leads us to linearly draw the accumulation of phase with bipolar gradients in the readout direction. However, with moving spins, the accumulation of phase behaves differently, and we have a net phase gain when we shouldn't. This is the non-ideality caused by the phase effect. So proceeding, we can see the phase effect formulation using Taylor series expansion. Here we expand the position term using Taylor series as the initial position, initial velocity, and the acceleration. As can be seen here, this corresponds to the addition of moments, giving the total phase accumulation. For our project, we are assuming a constant velocity in the blood vessels. So the also using the assumption that the gradients are constant in echoplanar imaging, we can take the derivative, which will give us a T2 squared term, as seen here. So the total signal equation is written with the usual kx and ky terms plus the additional velocity dependent phases, which will dephase the total signal. So we would like to approximately or intuitively get an idea of what these velocities do in each direction. So the phase caused by the Vy is written here, and we can rewrite it to be a function of ky. But since the velocity is a distribution in each pixel has a different velocity, it's position dependent, so we cannot easily take it out of the integral. However, we can approximately see the effect by assuming a constant and uniform Vy region in our image. And doing so will let us to take the Vy term out of the integral and see that the reconstructed image using the inverse Fourier transform leads to a shift proportional to the Vy velocity magnitude. However, the x direction velocity is not so simple. We can do the same derivation we did in the for the y case. However, this time we get a function of kx not that is not linear. It's it's a term with kx squared. So assuming a region with constant uniform Vx, we can take it out. However, this time the additional term does not amount to a shift, but a nonlinear phase, but can be imagined as a nonlinear phase filter. This will cause different frequency components of the image to be shifted different amounts, or rather phase in different amounts, which will disperse the reconstructed image if we reconstruct it using the inverse Fourier transform. Since the different frequencies are shifted this different amounts, the total structure of the image will be dispersed and spread out or smeared. Luckily for us, for most natural images have their frequency components concentrated in near and low frequencies. So the relative shift experienced by each frequency component is similar, but yet the small differences causes the smear effect. Additionally, the Vx enhances this smearing effect or dispersion. But once again, luckily, in our body, the blood moves at relatively low speed, such that the smearing or dispersion does not equate to a total moving artifacts, but just small blurs and shifts along the x direction. So I'll be lending the stage to Doğa Demirbağ.
Thank you, Artun. Another effect caused by the flowing particles is the time of flight effect. The time of flight effects are related to RF pulses. The tip angle of the RF pulse and the timing of the impulse are very critical in this point. And firstly, we have the signal washout effect, which we tried to observe in our simulation. It was based on that. In signal washout, since the particles are moving, some of them could not be catched in the excited slice. The loss caused by this movement and the particle loss is basically named as the signal washout. Another time of flight effect, we can say, is the inflow enhancement, also named as the signal washing. We do not directly observe the effect of signal washing in our simulations and project. However, we believe that it's important to mention the effect of this. Uh, in inflow enhancement, the movement of the newly incoming particles to the excited slide affect the magnitude of the reconstructed image. And as it can be seen from the hand-driven figure, we simulated a slice in the Z direction, which the particles are moving also. In our overall constant for the time of flight became 1 minus Vx times Te over 2 over delta Z. This will contribute to our overall equation as a constant and will affect the same magnitude of the reconstructed image. The mentioned overall equation containing both the phase and the time of flight effects is as follows. As you can see, this is our signal equation. And moving on to our data set. In our data set, we did not use an external image. Instead, we constructed our own flowing particle phantom. We wanted to model an obliquely standing blood vessel and took a slice to excite it in the Z direction. And we decided to generate an image where each pixel has their own magnitude and velocity values. By changing the velocity value, we were successfully able to observe the non-idealities caused by this motion effect. And now Daphne will continue.
Some of the assumptions that we made throughout the project. Firstly, we assumed a constant particle velocity, a sufficiently small echo time, and a sufficiently large repetition time. Our spin echo sequence is as follows, as can be seen from the figure. Our main simulation methodology was that we didn't use any external libraries nor any AI tools. Based on a single formula, we developed a formulation that includes both phase and TOF effects altogether. And we generated images including an impulse phantom, the profile of an angled blood vessel, and a combination of blood vessels with different velocities. Throughout some research, we found out that at the aortic valve, peak velocities up to 500 centimeter per second is possible for pathological cases, but a general case is around 150 centimeter per second. We based our velocities according to this information. Here you are seeing a impulse point source moving at 400 centimeter per second in X direction. We can see the dispersion and shifting effects happening, and also the smearing effect of the dispersion is present here. The frequency components of the point source are shifted different amounts non-linearly, creating a blurred and shifted image as expected. Here you are seeing same particle, same point source, but moving in y direction with the same 400 centimeter per second velocity. Here you're seeing combinations of motion in both direction, both 200 centimeter per second. And this is a profile of a vessel with blood moving it at 400 centimeter per second in the X direction. A larger vessel image lets us see a more realistic version of the blurring due to flow. And we see that for such vessel images, this flow speed is not sufficiently large to cause a noticeable artifacts, but more about blurring and signal loss due to dispersion. The difference image shows the direction of the motion as well. Here we did a exaggerated motion in the X direction, and as you can see, there are many artifacts are present due to the square term in the kx. As we go higher frequencies, the artifacts enlarges. And this is for the same motion at 400 centimeter per second in the y direction, as well as its difference. And this is again motion in both directions in x and y. And these are blood vessels with varying velocities in the x direction. As we go to higher velocities, the phase shift, the dispersion, and the blurring increases. Similarly, this same thing happens in the y direction. And here we are seeing varying velocities in the z direction. As it can be observed from the difference plot, the magnitude decreases as the velocity increases, and the main reason behind this magnitude loss is the effect of the signal washout. And these are references. Thank you for watching.